ASN Filter Designer provides ARM Cortex-M developers with an easy-to-use, powerful signal processing platform for developing real-time dataset cleaning filters and feature extraction filters for Internet of Medical Things applications. Looking at the main UI, we see that the real-time user interface allows you to graphically experiment with your design requirements by just using the mouse, meaning that a suitable digital filter can be designed and customized within minutes without explicitly entering any specifications. Let's change the sampling rate to 50 Hz to match our application. Although the Filter Designer UI is great for designing simple filters, we need a little more control over the parameters for our PPG filter. So let's move over to the live scripting language IDE. The IDE implements a sandbox, allowing for the experimentation of any type of filter, the so-called H2 filter. We refer to this scripting language as ASN filter script as it provides over 82 functions for mathematical operations and filter design. I've already implemented the code for a suitable filter, so let's have a look at the code in depth. The essence of the code centers around designing a low-pass FIR filter using the window method. I've used the Blackman-Harris window here as it gives high sideband attenuation. We then use the frequency rotation transform to convert the low-pass real filter into a complex bandpass filter. The interface variables are just used to set cutoff frequency, filter order, and center frequency of the bandpass filter, which we'll experiment with. Running the code, we see the filter is designed based on the interface variable's default values. Locking the axes and then zooming into our region of interest. As we're interested in eliminating the lower frequencies less than 0.5 Hz, we can use the ruler to set the target point for our 3 dB cutoff. We can tweak our interface variables and see the results in real time. Zooming into the 0 Hz region, we can fine-tune our null to give us the maximum attenuation at 0 Hz, which will remove our DC offset. Okay, this now looks good enough for our evaluation. So let's load a PPG comma-separated dataset file into the tool and see the results. Opening the signal analyzer, we first need to set the output math function to angle, such that the zero crossings method works on phase. Also, let's set the frame size to 500 samples, corresponding to a 10-second observation window. We now need to set up the data analysis method for determining zero crossings. Selecting the real outputs and the zero crossings method, we just need to specify a detection threshold. ±2 should be fine. Finally, let's turn on the frequency estimation algorithm and set the units to biomedical. Also, let's use median filtering instead of mean filtering to minimize the effects of outliers on the zero crossing estimates. And as we're just looking for the end of our sawtooth of our phase waveform, we just need to select down crossings. Taking a comma-separated value data file that we obtained via the SDS framework from prototype hardware or another framework such as an EVM, we can simply drag and drop the comma-separated file onto the canvas. The tool will then check the file for errors and eliminate the data, and finally open the signal generator UI. Clicking on the play button, the data file will be streamed through our complex filter. Adjusting the chart for DC offsets can be achieved like so. This looks good, however notice that the input and output data are misaligned. This is due to the group delay or latency of the filter. Returning to the main UI, we see that the group delay is constant and equal to 125 samples. Adjusting the signal analyzer display by this group delay, we see that the input and output now line up. Let's leave this filter to run on the dataset and observe the pulse rate estimates, which should be around 90 BPM. Very good. Now let's move to a motion artifact and see what the median filter does. As seen, it's quite minimal on the overall estimate, which is great. We can now deploy this filter to an ARM Cortex-M processor via the ANSI-C framework. Let's choose single precision quantization, as an M4F device supports single precision hardware floating point, and in many cases double precision is a little over the top. ASN's ANSI-C framework was developed with close collaboration with ARM's architecture team, which means that our implementation on all ARM Cortex-M devices is extremely efficient. Our framework takes the CMSys DSP library implementation a few steps further by fully supporting complex filters in the ASN internal filter cascade and math functions. Although data analysis options such as zero crossings detection and frequency tracking are not part of the framework, as they're application specific. The default ANSI-C project is based on the open source CodeBlocks IDE, allowing developers even on a shoestring budget to get their applications up and running without any hassles. This code of course can be used in Microvision or STM32Cube or even any other IDE supporting C99. Opening up CodeBlocks, we see that the tool has generated a streaming application using a sine wave as an input. Data is handled in blocks, which is in line with the ping-pong buffering concept. Notice that the code generators also support Python, MATLAB and C#, so you can export your design to other environments using our frameworks very easily. It really is as easy as it looks.